Hello, Honors Chemistry, and happy Tuesday. So, as you know, I am not here today. I have a personal day. But I wanted to make sure that you had plenty to do and lots of learning that could occur. So I've got some notes for you as well as some practice, because we do have a quiz on Friday. Yay! So we're going to start out with a bell work. So please tell me what type of reaction this is. And you have a couple of minutes to figure that out.
Up on the housetop, reindeer paws, out jumps good old Santa Claus, down through the chimney with lots of toys, all for the little ones' Christmas joys. Oh, who wouldn't go? Who wouldn't go? Up on the housetop, click, 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 down through the chimney with good Saint Nick. First comes the stocking of little Nell. Oh, dear Santa, fill it well. Give her a dolly that laughs and cries, one that can open and shut its eyes. Who wouldn't go? Who wouldn't go? Up on the housetop, click, 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 down through the chimney with good Saint Nick. Look in the stocking of little Bill. Oh, just see what a glorious fill. Here is a hammer and lots of tacks, a whistle and a ball and a whip that cracks. Who wouldn't go? Who wouldn't go? Up on the housetop, click, 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 down through the chimney with good Saint Nick. Ho, 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 who wouldn't go? Ho, 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 who wouldn't go? Up on the housetop, click, 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 down through the chimney with good Saint Nick. Down through the chimney with good Saint Nick.
Okay, so let's take a look at this reaction. So, if we go through the different types, right, a synthesis reaction would start with 2 substances or more and end with 1, which we definitely don't have. A decomposition would start with 1 and then break down into 2 or more, which again, we don't have. We have 2 and we end with 2. A single displacement would start with an element and a compound and end with a different element and a different compound. So, we start with sulfur, which is an element, and iron 3 oxide, which is a compound. We end with iron 2 sulfide, which is a different compound, and oxygen, which is a different element. So, we're looking at a single displacement reaction for this one. Alright, so we're going to move on. We're going to do some notes up next, so please take some time and write this down. guys. So hopefully you've had time to write this all down. And if not, well, you're just going to have to listen to me as you write. Or pause me and then, come back when you're done. All right, so today we're going to be going over reaction rate and equilibrium. And to do that, the first thing you have to understand are what are called reversible reactions. And just like they sound, they're just reactions that can change directions or reverse. All right, so if we take a look at this first equation, which is water plus oxygen yields hydrogen peroxide, okay, we can also know that if we take hydrogen peroxide, it can yield water and oxygen. All right, so because both of these are true and they're the reverses of each other, rather than writing two separate equations, we can just write them together as one with a reversible arrow. So there are a couple of different ways to show that an equation is reversible. So there's the two-sided arrow, like is shown here. There's also just drawing two separate arrows going in opposite directions. Or, my favorite, are two half arrows. So all of those mean that it is a reversible reaction. And what that means is that you can either take the reactants and form the products, but you can also take the products and they can form back to the reactants. Okay, so one important thing with looking at reaction rates and such today is that all reversible reactions reach what's called equilibrium. And we'll go over that a little more in detail in a minute, if it's left undisturbed. But it's very rare that they're left undisturbed. And again, we'll talk about that momentarily. So first, equilibrium is when the amount of reactant and the amount of product remains constant, even though the changes are occurring. So remember that with a reversible reactant, or reversible reaction, you're going from reactant to product, and product to reactant, reactant to product, and product to reactant, back and forth, back and forth, back and forth. When it's at equilibrium, you have the same amount of reactants and the same amount of product, so they stay constant. Okay. A specific type of equilibrium is known as dynamic equilibrium, and this is specifically when the reactants and products form at the same rate. So usually, when you're looking at the back and forth, like we do here, the rate isn't the same, it's just the amount on each side that stays the same. When you have dynamic equilibrium, the movement in both directions is exactly the same rate or speed of reaction. Okay, so remember too that if you have any questions on any of this that come up, you can email me at mrs.horn, that's an O, .fhs@gmail.com. Or send me a message on Edmodo. We will also go over this tomorrow if you have any questions, so don't worry. Alright, so on to our next page. We're going to take a closer look at equilibrium. So please take a minute and write this down. Alright, so let's take a closer look at equilibrium. So when a reversible reaction is at equilibrium, as long as the system goes undisturbed, it will stay that way. But if you disturb the system, it'll cause what's called a shift. And a shift is a movement of the reaction rate, so a speeding up in one direction or the other till it gets back to equilibrium. So according to Le Chatelier's principle, and he is a French chemist, the reaction will shift to the direction that fixes equilibrium. So it'll either shift to the left towards the reactants or the right towards the products. And the way you figure out which way it shifts is looking at where you add or remove something. So if you remove a product or you remove a reactant, that just means you're taking some of it out of the system. The reactions are still going, but you've removed a little bit of one or the other. So if you remove something, it's going to shift to the same side, left or right, of a removal to replace that loss. So if you remove from the products, it's going to shift to the right. If you remove from the reactants, it's going to shift to the left. Okay, we'll take a look at exactly what that means momentarily. Okay, it's also true that a reaction shifts to the opposite side of an addition to use the gain. So if you get extra reactant or extra product, it'll shift to the opposite side, so away from that addition. Okay, so let's take a quick look at what that means through an example. So please write this down and we will go over and fill in the which direction it shifts momentarily. Okay, so let's take a look at shifting equilibrium. So in this reaction, I've got magnesium and oxygen reacting to form magnesium oxide and energy. This also means that if I add energy to magnesium oxide, that'll form magnesium and oxygen. So what we need to take a look at is what happens when I add or subtract any of this from either side. All right, so if I add magnesium, that means that I am adding something to the reactant. So I have more of this than anything else. When that happens, right, it's going to move to the opposite side. So since I've added on the left, it's going to shift to the right, right, because it shifts away from that addition, or to the opposite side of that addition. Okay, so staying on those lines, if I add magnesium oxide, right? I've now got more of that than anything else. So it's again going to shift to the opposite side of the addition. So I've added on the right, which means it's going to shift to the left. Okay, and then removals work in exactly the opposite way. So where with addition, it shifts to the opposite side, with removal, it shifts to the same side. So if I remove O2, that means I've suddenly got less of it over here. Okay, it's going to shift to that same side, so it's going to make more O2 to kind of fill in that gap. So this one is going to shift to the left. Okay, but if I then look and I remove energy, or the energy just escapes, okay, the reaction now is making less energy, so to fill in that gap, we have to shift to the right. So when you're looking at shifting, all you will ever have to say for that is either shift to the left or shift to the right. So the biggest mistake people make on this is that they think that it always shifts in a certain direction when it's added, or it only shifts in a certain direction when it's removed. Remember that it's going to depend on which side of that arrow you add or remove as to which side of that arrow it will shift to. Alright, so this is your last slide for today. So please take a couple of minutes and write this down. And we will do an activity, not today, because you guys decided you didn't want to have that kind of responsibility. But we will do an activity for this when I am back on Wednesday. So go ahead and please write this down. Alright, so let's go over this. Now, we're going to discuss 4 factors that affect reaction rate. There are more. One that we will not talk about today is pressure. But we will talk about that when we look at gases and gas laws. Okay, but today we're going to look at 4 pretty common ones that we use on a pretty regular basis, either in the chemistry lab or in real life. The first is temperature. So, when you have a higher temperature, that means your particles are moving faster, and that gives you a greater reaction rate. The reason for this is, in order for a reaction to occur, particles have to hit each other, and they have to hit each other with enough force and at the right angle in order for a reaction to occur. If you've got particles moving faster, the likelihood of this happening goes way up. Okay, and we've all seen this happen before. Okay, we all have had that day when we took the milk out of the refrigerator and we left it on the counter. And we get up the next morning and we open it, and it's no longer milk of any sort we want to drink because it's now all stinky and gross. But if we would have put that just back in the fridge, it would have lasted longer. Okay, and the only difference between those two instances is the temperature on the counter is higher, where the temperature in the refrigerator is lower. So that increased temperature speeds up the particles and makes it more likely to react, and in the case of here, decompose and break down and rot. Okay, so that's why you get that smell of rotting milk. Okay, the next kind is concentration. So, with concentration, the higher the concentration you have, then the more particles you have. So, in a small space, if you only have two particles, the likelihood of them hitting each other with enough force to make a reaction occur is relatively low. But the more particles you put in there, the more likely it becomes that they're going to hit each other. So that's where that more particles comes into play. And this gives us a greater reaction rate. So the higher the concentration, the more likely, again, they are to hit each other, the higher the reaction rate. Okay. And this is similar to, or is also shown in surface area. So that's where that little star refers to. Okay, when you have a greater surface area, it means that you also have a greater concentration. For example, if you have a log and you have a pile of sawdust, and both of which have the same mass, so you have the same amount of wood, which one is going to be more flammable? The wood or the sawdust? The sawdust. Right? You're going to get huge flames from sawdust flying around, where it's going to take a while to get some flames from the wood. The reason for that is with the wood, the only place that you have surface area is on the outside of that log. So those are the only places that can react. With sawdust, on the outside of every single particle and surrounding every single particle, you've got surface area. So that allows the reaction to happen more swiftly. Okay, so we see this when we do reactions with higher concentrations of things like acid. So a 1 molar hydrochloric acid will react much slower than a 10 molar hydrochloric acid because of that concentration. Okay, so those are things about the amount or the temperature that you can change. There are also things you can add to a reaction to either speed it up or slow it down. The first is a catalyst. So catalysts speed up a reaction without actually taking part in the reaction itself. So an example of this would be enzymes in your body. Okay, enzymes speed up digestion. Without them, you would eat your food, they would go through your body, and you would get no nutrients from them whatsoever. With enzymes, it speeds that up so you can get vitamins and minerals and all of those things, protein that you need. Okay, you can also add catalysts to speed up a reaction that you want to see that usually goes slowly, and we'll use these and have used them in class. The other side of things are inhibitors, and these slow things down. Okay, and the same with a catalyst where it doesn't take part in the reaction, neither does an inhibitor. It just slows it down. And these are used all the time, especially nowadays, in foods. Okay, and we put things like BHT in our food to preserve it. Okay, so we use preservatives. And preservatives are inhibitors. They slow down the breakdown of the food. So they slow down that decomposition reaction. Right? Food, like cereal on the shelf, that contains a preservative is going to last months and months and months longer than something that's fresh, okay, like the bread on the shelf. Okay, that's going to break down a lot quicker. So these are things we add to the reaction in order to speed it up or slow it down. This is something we do about the reaction to speed it up or slow it down. And we will do a lab based on this, or at least an activity based on this, okay, on Wednesday, so tomorrow when I get back. Alright guys, so now that you're done with your notes, we've got some other things that you're going to be doing. So first of all, we have some information in another video. Yay, another video! And in this video, you're going to look at the reaction rate. And this is going to show you how surface area works. Okay, once you've watched that video and you're done, feel free to discuss so you understand it. And if you don't, again, send me questions or ask questions tomorrow. Okay, you're going to have 2 worksheets. Okay, the first worksheet talks about reaction types. The second talks about reaction types and rate. And then when you're done with those, I do have the quiz reviews available. Now, on those quiz reviews, on the last page, are the anchor activities. So if you wanted to get started on those early, you could. And those are on the last page. Alright, so thank everybody very much. You've been a great audience. And I want to thank you for being good for your sub. And I want to thank Mr. Healy for helping out and keeping an eye on you guys. So I will see you tomorrow. And have a great rest of your day.